Hello and welcome. Today we're going to do an example double integration problem over a non-rectangular domain. Alright, so let's just get this one off. I want to make this a very straightforward and simple first problem to do in this type of problem. So what we're going to do is we're going to do a non-rectangular domain. We're going to do a triangle. So again, a fairly straightforward problem. Alright, so what we have here is we're going to say it's a triangle, and it's going to be x going from all the way out to 3, and then the y, the height of the triangle, will be 2 high, like that, as follows. Okay, so we're in the plane here, and we'll say that our domain that we're going to integrate over is D, and it's this triangle here. Okay, and then so we have we'll call that set D, and we have a function we want to integrate over. We'll say it's x squared times y. Again, this is just going to be a very straightforward problem. First problem to solve involving integration over a rectangular domain. All right, so the goal is we want to do the double integral of of f of x comma y over the domain D dA. Okay. All right, so we have two choices here. We have dA equals dx dy, or dA equals dy dx. So here we're going to do, with the first option, we're going to do x first. And for the second option, we're going to do y first. So either way will work about the same in this particular problem. So I think for this particular problem, we'll go with this one first. I think that'll be a nice one to try. So let's remember what that means. So let's visualize what we're doing. So what we're doing here, if we're integrating x first, we're basically integrating via horizontal rows like follows. What you do is you fix y at a particular value, in your domain, and then integrate along a horizontal row. So in this case, we can take y to be a specific point there, and we're going to start right there at the beginning, right at x equals 0 there, and then we're going to go out and integrate along there in a one-dimensional integral till we hit the other boundary on that diagonal line there, and then of course we're going to move y over an increment and do it over again. So we'll go up here a little bit and integrate out until we hit the next boundary, and so on and so forth, and keep doing that like follows. So we keep incrementing y up until we've integrating all these rows. So in many ways, this is sort of like how a farmer harvests a field in their tractor. Is that you would be cutting and harvesting your crops along rows until you cover the entire space. In this case, we have a field that's a triangle. You're going to go from the x equals 0 point out to some x limit, what I'll call the right limit. And that right limit is clearly going to depend. It's going to depend on y. Okay, and what I mean by that is if I pick a certain y value here, and I'll just make up here, clearly we're not going as far, but if I pick a lower down y value, there's going to be a longer row. Okay, so that's the kind of high level approach we're going to take. So what we have to do is figure out basically what is the what we got to define first, and I always like doing this, is first thing is to define D explicitly. In fact, on my exams, I typically ask students to do this. I find that if students get good at defining D explicitly, then everything thereafter will be easier to do. This is usually the crux of double integration. So we always start off our set by saying what kinds of things are in our set. And so in this particular case, what we have here is basically x, y pairs. And of course, we're talking about a set of coordinates x and y, so we need to specify that's the kind of thing we're talking about. The next thing we need to do is say that, well, what does y vary over? So y, of course, it varies from 0 up to 2. All right. But then for those particular y values, we have to say what x varies over. So we know x never goes below 0, but it clearly doesn't go, it has a line. So we have to figure out what that line is. So I'm going to draw that line in red here, going down like that. So that line of the hypotenuse, we can figure that out. Well, it clearly has a slope of negative 2/3 times x, and then, of course, it has a y-intercept of 2. So that's our line of hypotenuse. You can think of that in terms of the farmer's field. That's basically going to be that right fence that ends each row. Okay? Again, that's the metaphor we're using to understand what's going on with this triangle here. All right, then, so again, if I fix a y, what I need to do is find x limit. Again, this fence. So what we have to do is basically invert this function. So we're going to have as y minus 2 is equal to negative 2/3 x. And then we're going to go a little further and say x has to be equal to negative 3/2 times y minus 2. We could re-express this as negative 3/2 y plus 3. That would work just fine as well. All right, so this is going to now represent what x cannot exceed. So I'm going to take that and bring it right up there and define my set this way. So there's my set. And this also defines the limits of integration. All right, so to finalize what we're saying here, I want to build an integral. I need to build an iterated integral. What we have here is this abstractly defined double integral, and now we have to fill in all of these question mark boxes here. All of those things are going to get filled in, and now we can finally do it. We know that dA is going to be dy dx, or sorry, dx dy. So that's our dA. The next thing we need to do is write out what the y integrals. We know the y integral is going to go from 0 to 2 for y, and x is going to go from x up to 3/2 y plus 3. And finally, the function we're integrating is going to be x squared times y. That was defined in the original problem. So right here, this is going to be our iterated integral. All right, so this is all the work. I think this is the crux of these double integration problems, is setting up the iterated integral. Okay, now we can go on to actually compute it. Let's do that on the next page. Okay, to do the iterated integral, of course, we have to break this into kind of a nested set of single integrals. Again, I'm being very pedantic here. I've been saying, okay, now I'm going to integrate this first. But we're going to fix y as a constant while we're integrating over x. Okay, we can do that as follows. And again, as I write, I keep my dy integral. I keep that on the outside. I'm not doing anything with that. But again, y is my antiderivative, or y is my constant, and then the antiderivative of x is going to be x to the third power over 3. And then we're going to evaluate at our limits of integration, like this. But what we have to do here is we have to be mindful that we're setting x equal to this thing, all right? Again, y is a fixed number. We're not messing with y. So what we do here is plug in for the x value there. All right, let's do this. That's our integral that we're going to do now. We could use we have to multiply this out. Or what we can do is we might be able to actually simplify this a little bit. It might be helpful to do that, a little simplification here, just to help smooth things out a little. It doesn't really matter. What I'm going to do instead is I'm going to do actually a U-Substitution. Either way you do it, it's fine. So I'm going to say that u is equal to negative 3 halves y plus 3. And then du dy is equal to negative 3 halves. And so that means that negative 2/3 du is equal to dy. So anywhere I see a dy, I can put a negative 2/3 du in its place. And so now we're going to have our integral is going to go from 3, and it's going to go up to, let's see this, if I take y is equal to 2, I will get 0. And then I have a negative 2/3 there. And then I have a u to the third power. But now what I have to do is solve for y. So now I have a u minus 3 times negative 2/3 is equal to y. So now we have to write that there. What's nice about this is this cancels, and we're left with a. And now I see my limits of integration are kind of backwards for what we normally like, so I'm going to change that around by changing the sign of the integral and also changing the order of limits of integration. And we're going to get here now a 3u cubed minus u to the fourth power du. And now we can solve this thing all the way through. All right, so the rest is arithmetic. I'll let you calculate what that number is. And and figure out the value there. But what's really important is we just have our procedure correct, and we've done our double integration correctly. Again, the big step, I will just emphasize this over and over again. The most critical step is defining your set. Figure out what that is. That helps you determine the limits of integration. Without doing that, it's very difficult to get started with anything else. So anyway, I hope you enjoyed this video. I'll see you in the next example. Thank you very much.